All right, good afternoon, everyone. Just going to take a moment and go back through our PowerPoint, make sure everybody understands it. The information we did cover in class. I know third period we didn't get a chance to go all the way through it, but we're going to backtrack down and just make sure we have all the information we need. Now, again, our learning targets for today: describe the parts of a wave, explain the light that consists of electromagnetic radiation, and explain what causes an atomic emission spectra. Again, these three things you should be able to do when you finish this video. If not, you want to make sure you write down questions that can help you to be able to do these different things. Now, starting off with parts of a wave. First definition that we actually dealt with: wavelength, looking at the distance between the two crests. So, if I go here, this overall is my wavelength. This cycle here is my actual wave from here to here. Now, taking this information a little bit further, we want to analyze and see what's going on with the actual wave. The high point itself is what we call the crest, the low point, the trough, and the distance underneath the curve of the wave is what we call the amplitude. I can adjust the amplitude based on the amount of material that I have to make my wave, how fast or how far it's going. But we're going to go and use this now to apply it to light. Now, the light that we see every day, all these different colors that we experience, from reds to oranges, all of them are basically just waves of light that are being reflected. Well, what do I mean? The light that we stand under most times in buildings or even under the sunlight, when we put it through a prism, one of the things that was found is that it's actually made up of multiple different wavelengths. And that's what we're seeing here. This band from 700 all the way to 400 nanometers is the area of visible light that we actually see. Now, this visible light is a part of what we call a continuum of electromagnetic spectrum. So it's not the longest waves, but it's also not the shortest that we deal with. It's just in a range where our eyes can actually pick it up. They talked about the fact, studies have shown that dogs can actually see a little bit into infrared, and many animals actually do this, and it's beneficial for their survival. Whereas for us, the visible spectrum is what we need the most of. Now, notice as we start with radio waves being our longest, going all the way down to gamma waves, what happens to the wavelength? If you said that it gets smaller, you will be correct. It gets shorter and shorter, and as this happens, we start to notice some other patterns emerge. The first is, the longer the wavelength that we have, the lower the frequency we're dealing with. This is why radio waves, when they pass into your car or into your room or any of those things, don't affect you, because they're so long and the frequency is so low that it actually doesn't do anything to the cells in your body. Now, these also have very low energy. So we would say there's an inverse relationship between wavelength and frequency, meaning when one goes up, the other goes down. So long wavelengths, low frequency. And if we shorten the wavelengths, we get much higher frequency. So again, inverse relationship or opposite relationship: shorter wavelengths, high frequency; long wavelengths, low frequency. Now, the other thing that we're going to consider is the relationship to energy. If you notice here that low energy is also going to be associated with long wavelengths. Because it takes so long for the wave to go through, again, it doesn't do much damage as it travels. But if I have short wavelengths at a high frequency, that means a lot of them are going through very quickly. It's going to have a lot of energy and can actually do some damage within my cells, causing them to mutate or other things like that. So with that in mind, we keep moving. Now, we talked about Niels Bohr and his discoveries around 1911, somewhere around that range. Now, they noticed that when he put certain elements in the light, in a flame, they actually gave off a different color. And he was trying to figure all this out and understand why this happened. The more research they did, they started to see that it's actually related to the element's electrons. There's something about those electrons that allows it to give off a different color when you heat it up. And he wanted to figure out what exactly it was. So he borrowed a little bit of a little bit of knowledge from some other scientists. They looked at the fact that light itself is just energy traveling through space. And second, they started to notice that light itself can act in two ways. So it can act as a wave and as a particle, all at the same time. Now, this is what we normally think of when we think of light behaving as a wave. We think of the white light going in through the prism and separating and seeing the different colors. We think of the actual light of our sun. As it goes out, it passes by our planet. It's still able to wrap around our planet and to hit things beyond. So that's how we're able to see some of the things that happen out in space. And just in general, if we take a flashlight or something small and put it up against, say, your table, you would start to notice that we have something going on here. The light itself still bounces off and it's still able to go around to different locations. Now, if we go on to the next phase, this is how we're able to figure out that light also behaves like a particle. Now, Albert Einstein, we all know him, he discovered that if I change the wavelength, as I adjust it and the wavelength gets shorter and shorter, it's going to pack more energy, and eventually I'll actually have enough energy to remove electrons from the surface of a metal. So if we're looking here, we have potassium metal that we're actually looking at. There's a certain threshold that we would have to meet in order to remove electrons. When we look at 700 nanometers, it's not enough. No electrons are ejected. But coming down to about 550 nanometers, very, very small length, we notice that we start to actually remove electrons. How do we know? Well, take a look at this number here, 2.25 electron volts. This is letting you know how many electrons are really being removed, or how often they're being able to be removed. Now, if we shorten the wavelength even more, we're able to eject more electrons. So again, this is going back to that relationship between energy and frequency. So this equation here says the frequency times Planck's constant, which is dealing with the actual energy to remove to move electrons in general, will give us the energy of the actual photon or light particle. Now, these photons or chunks that we're looking at can behave as a particle of light. When it hits our electron, which we know has mass, which actually has size, it causes it to jump to another level. That's what we're seeing happen as it goes from I to J. It jumps up a level. Now, the absorption at the quantum level happens when the individual photon has the exact energy that corresponds to an energy gap between two possible energy states. The type of energy gap corresponds directly to the frequency of the photon. That sounds like a lot of wording, but basically what it's saying is each of these lines that you see here has a particular energy level. The energy that's coming in on the wave has to have enough energy to get the electron from here, from the starting level, to whichever level it's going to go to. If it only has enough energy to get it to level 1, it can't jump to level 4. It'll only get this far. If it doesn't have enough energy to even get it to level 1, we'll have nothing that happens, or we won't see the response of any light being given off. Now, Niels Bohr started putting all of these ideas together. He took a little bit from this guy named Max Planck. He took a little bit from Einstein, and then he shined light from hydrogen gas through a prism. And instead of getting a full spectrum like we saw before, he got these different lines. And he was trying to understand, why is it that we're getting these lines? It just doesn't make any sense. Well, what he started to realize is, hey, those energy levels that we talked about, they actually gave off different colors when the electrons came back down. I wonder. And so he started to calculate the energy associated with each of the wavelengths that he was seeing, all of these different colors. And he realized that, hey, these must be the thresholds of the energy levels. So if this is what's telling you to get to level 1, level 2, level 3, level 4, and so on. And he was able to connect and show that the atom itself actually had some type of organization within it for those electrons. They weren't just scattered about like, chocolate chips in a cookie. No, they actually had specific places, specific energy amounts, so that the electrons would go to these different areas. Now, not all spectra are actually visible to our eyes. There are some times where we'll look and we won't get a response. Does that mean that nothing happened? No. It just means that the transition may have been from one level, from a very, very high level to a very, very low level, and it falls within a range that is not visible. Like we're looking here at what we call the Lyman series. As we had transitions from the highest level down to the first level, many times we fell right outside that range of visible light into the UV or ultraviolet area. When we look at the, I guess it's called pass-spin series, notice that these are falling a much shorter distance. In doing that, they also fall within a range that we can't really see. These fall within what we call the infrared area. So these are areas that are very, very close to visible light, but they're not visible light. Then last but not least, we have the Balmer series. And if you're taking a look at it, these are giving us colors that we actually see, a red, a green, and a blue. This corresponds to what we're seeing here, the transition from 3 to 2, from the 4th energy level down to 2, or from the 5th energy level down to 2, giving us colors that we can actually understand and see and determine the energy for them. Now, what I want you all to do, take your notes, take a look at everything that we have, and then see if you truly understand it. How will you know if you understand it? Well, if you rewind the video and go back to the learning targets, you should be able to do those things that were listed before. If not, I want you to write down some questions so when you come into class tomorrow, we can discuss it and make sure that you understand this concept. Okay? Now, with that being said, say have a good night. Again, write down any questions you have for me, and I will see you tomorrow in class. Have a great day.